first presentation we're going to do a little differently. We're going to split it between Kim and Paul. And so we'll have a couple of like 20 minutes, and then we'll have a little question for Kim if you got, because hers is very specific in one area. And then Paul will give his presentation in another area. So we'll have 2 sets of question time periods for everybody. And then we can have some more questions if you want to ask either one later. So Kim is going to go first. Kim is associate professor at University of Minnesota. She's worked there on swine viral diseases for the past 10 years since she's gotten her PhD at UC Davis. And her research is focused strongly on the PRRS side, looking at the evolution, classification, epidemiology, and the dynamics of PRRS and how it spreads through the population. So we're going to start with that. And then Paul, of course, we know from the Swine Vet Center, been in the industry for a long, long time to see the before, during, and where we are today. He's been involved in the disease management and elimination, and he's, of course, had his awards on the Howard Dunn and the Swine Practitioner Award from ASV, as we remember. He's a senior member at Swine Vet Center. It's at 15 veterinarians, and started the clinic in 1991 through it says here 3 veterinarians, but then they needed 1 extra after 6 months later. So Paul's interest in veterinary school has been since he started his family farm with his family farm in southwest Iowa, and remembers working as veterinarians as he's treated the hogs and other livestock. In high school, he worked in the confinement operation, which kind of sealed his focus on how he's gone since then. Paul went to Iowa State, earned his DVM there in '85, and then switched to the Swine Vet Center when it started in 1991. So over the years, he's done many things. As people have known Paul, he's been involved in all aspects of the swine production and the business part, and it's focused mostly on disease elimination in the areas of mycoplasma would be the most recent one. He enjoys problem solving and making elimination and trying to achieve the best that we can be on the health side on a farm. So with Kim's focus on helping us understand the virus and how it moves and what we need to do, and then Paul's application of, here's how it works in the population, the field setting, this should be a really nice part of the section. So we'll start with those 2. Kim will start first, and then we'll go with Paul after that. Okay. And Caesar told me that's forward, reverse, and...
All right. Thank you so much, Dr. Moore, and thank you all for being here. It's my pleasure to be up here with Paul, talking about an initiative that we've been working on for the past several years on fine-scale genetic classification of PRRS. And I have heard this called Kim's classification, but that is not what I would like it to be known as Kim's classifications. This is the product of a working group that's underneath the umbrella of the ASV PRRS committee. And there's a large number of other people that are part of this working group and have been part of devising this fine-scale classification system that we'll be talking about today. So when you talk about PRRS control, or generally the dynamics of PRRS virus in the United States, like many RNA viruses, we are faced with a challenging virus that changes very, very rapidly through evolution. And what this means that although year over year it appears that our PRRS incidence or prevalence remains relatively constant across time, if you peek beneath the hood of what's actually going on is that every few years we get the emergence of some sort of new genetic variant of the virus. That new virus goes through a period of exponential growth as it spreads through the industry, and at some point it hits its peak, and the population size of that virus starts to decline as some new PRRS genetic variant then takes over. So we can observe this has happened repeatedly over time, which poses a problem of why we can't keep up with PRRS evolution. PRRS is also an interesting virus because it is also one of the most sequenced viruses in the world. This is a tabulation of publicly available sequences, and you can see PRRS right there, PRRS type 2. And it's certainly the most sequenced veterinary pathogen, but also publicly available is just shy of 40,000 sequences available on GenBank, but we know that the majority of data for PRRS actually sits in diagnostic laboratory databases. And the reason for that is, unlike other viruses where sequencing is more of a research tool or maybe a surveillance tool, for PRRS, we are actually generating data by animal health professionals that they're using to make day-to-day management decisions or monitoring of a disease on the farm. So we have an enormous amount of diversity, and we have an enormous amount of data. So that really brings me to a brief overview of how we classify PRRS type 2. And I'll just do a quick run-through of existing ways we can do to classify viruses as either the same or different is usually our goal here. We could calculate the genetic distance between two different genetic sequences and generate a homology table or a table of genetic distances. This is a great tool. It gives you a nice % difference. The challenge here is, well, first, we don't have a good cutoff necessarily of saying, well, if it's X% different, it's a different virus versus the same virus. But more importantly, I think the challenge of using genetic distance is that someone needs to collect all those sequences. There's a data sharing hurdle here. That might be easy if it's the same system, but if you're talking between two different production systems, that's potentially a hurdle. So we have to share the data. Someone has to put those sequences together in a bioinformatic program and generate the data. So it can be cumbersome, and then the other challenge is, well, what do you call it? How are we going to refer to this virus in the field? We need to have something to call it so we can start communicating about it in the field. So in the past 25 plus years, the method of choice to label viruses is RFLP types. And many of you I know are very familiar with RFLP types, but the issue with these is that they are an unreliable label of whether or not two viruses are actually related to each other. You can have two very different viruses that receive the same RFLP type, and you can have the same RFLP type assigned to viruses that are actually quite different from each other. So it's not a very good tool, and people have been complaining about this issue for well over a decade, and yet we still use it. More recently, the use of phylogenetic lineages has become popular. Essentially, this attempts to group viruses into kind of their ancestral family groups based on the OR5 gene. And all of these methods are essentially based on OR5. So let's take the example of the 1C144 variant, also known as 1C.5. This is our most recent variant of concern in the industry that's been circulating for about 4 years now. And let's see where this falls into our tree and how we might classify it. First of all, from this tree, you can see that the majority of sequences in the US belong to lineage 1. And then lineage 1 can be further subdivided into sublineages. And right now we have 4 sublineages that are the most prevalent sublineages for lineage 1 in the US. And then I know it's a little bit small, but I have written there that 56% of 144 viruses belong to 1C, but 28% of 144 viruses belong to lineage 1A, which is a completely different part of our genetic diversity landscape. And then we have 144 viruses that are found elsewhere as well. So again, highlighting the issues with RFLP types. Even if we zoom in to lineage 1C, at the period of emergence of this outbreak, the outbreak variant that we're interested in is in red, right? So it's only a very small sliver of the overall diversity of 1C, which is why even using the lineage in combination with RFLP types is not necessarily getting us to being able to identify which sequences are actually part of that emerging outbreak situation at the time. So all in all, the current methods do not meet stakeholder needs for epidemiological monitoring. And that's really the motivation of this working group, which was to explore and establish a fine-scale classification system for PRRS type 2 genetic variants in the US, and a system that's going to be able to be expandable as new genetic diversity continues to evolve. And I will note that this still is based on OR5, because that is still the sequencing that's being done in the vast majority of cases. We have funding from ASV and USDA to do this, and the system that I'm presenting today, which I'm referring to as lineage variant classification, has been beta tested by the U of M VDL. So some of you, if you have sequencing done at U of M, you may have seen some of these new variant labels on your reports already. All right, so to land on this classification scheme, we trialed numerous different approaches with a national level data set of almost 30,000 sequences. We selected the best approach based on the reproducibility across different analyses with different data, as well as the robustness of the approach during beta testing of kind of a prospective implementation of the program. So we started with data across 7 years. At the beginning, we began implementing the system, and then we added data every 3 months to kind of simulate this is what it's going to look like as we move through time. We just want to make sure that the variant IDs and classifications that we create are holding up through time and make sense through time. These two trees are the exact same tree. This is sublineage 1H, just to give you an example. On the left, the tips are colored by RFLP type. And I know the color's not super crisp on this screen, but essentially most of those sequences are either 184s in purple or 144s in pink. And you can see that the colors are completely scrambled up in terms of basically indicating the RFLP type is not giving you great information on which viruses are actually related to which other viruses. In contrast, when we look at the same set of data, now colored according to their variant ID, the colors are nicely differentiated from each other. We don't see this mixing of colors, and it also well aligns visually of what we would look at that tree and say, yeah, these look like groups we would see in the tree. So we don't aim to replace lineages or sublineages. I think that they're very useful still for understanding like the macro trends of what's going on. So we are incorporating this as kind of a variance as an additional level of classification that's below the sublineage level. So in this tree on the right, in the colored bars, these are our different sublineages. And then you can see within each sublineage, there's numerous variants that are colored in different colors that are nested within those sublineages. And so sequences belonging to the same variant have an average genetic distance of around 2.5% from each other on OR5. But that's an average, right? So they can be higher. We can see values as high as 5%. Variants are typically 5% different from the closest related variant. And then every 3 months, we take the new data that's coming into the MSHMP data set, which represents around 55% of the industry. And we take the new data and we update the system with these new sequences. And new variants are systematically defined using a set of criteria. So this is how we're going to expand as new diversity continues to evolve. And this also means that the number of active variants at any point of time is dynamic because we have the frequent emergence of new variants and the extinction of old variants across time. All right, the nomenclature that we have adopted incorporates the lineage and sublineage. So here we have a lineage 1H variant and a lineage 1C. And then we use an integer as the variant designator. So 1H5 and 1C5 are the 5th variants identified within their respective sublineages. And then as we identify new lineage, we just take the next number in line. So 1C5, 1C6, 1C7, right? So we just use the numbers in order, which also means that 1C5 and 1C6 are not necessarily more closely related to 1C5 and 1C7. All right? So that's the nomenclature that we've adopted. We also have built a web tool, which you can access here. This is both available to the D labs to classify new sequences that are generated. We don't need to repeat this whole analysis every time or wait 3 months to get the variant IDs. You can upload a sequence to this website, and it will give you the predicted variant that those sequences should belong to. So this is what it looks like. There are 5 sequences I uploaded here. The column to pay attention to is this assign.final column, which is the final assignment given to your sequences. These were all listed as 1C23. We also have the probability that each sequence belongs to that particular variant. And if this probability is below 25%, then we interpret this that we don't really have high confidence. We're going to call that sequence unclassified. So you will see unclassified sequences in this system. We also have listed the second most likely, or the second best match for each sequence to kind of understand, well, what this might be confused with. And then we have the probability that it belongs to that second best match as well. Just a disclaimer here, we based this system on US sequences from 2015 to present. So if you feed in sequences from before 2015 into this, or you feed sequences in from a different country, they're probably going to come back as unclassified because our system is based on the diversity that is in the US during this time period, which is going to be different than what you're going to find elsewhere or before then. That being said, we could use the same basic framework and approach to expand to other countries, and that's something that there's a lot of interest in doing. Another piece of information that you can find on this website is a list of all the variants that have been defined and some basic information about them. So for example, there's a column that lists all the modified live vaccines and which variant IDs are the vaccine-like sequences for each of those vaccines. We also have the percent of sequences from the last 12 months that belong to each variant, so it gives you some idea of their occurrence recently. And then we have the occurrence trend in the US, which is basically in the past 12 months, has the occurrence of that variant doubled or more than doubled, which we mark here as accelerating, or is the occurrence of that variant decelerating, which is decreased by at least half. So there's some level of information about the epi picture there. All right, so I want to return to why we're doing this, what factors we considered in kind of tailoring this system to meet practitioner needs. We did a survey with, that was administered through ASV a few years ago where we asked animal health professionals to rank the top 4 reasons for which they submitted samples to be sequenced. And these are the results of that survey, and the main ones were to discriminate between previous and new strains on the same farm or in the same system, determine the possible source of introduction, and anticipate and track the spread of novel variants. So I'll give you a few examples here for each of those reasons to kind of show you how the system is performing and how it might compare to RFLP typing. So first, discriminate between new and previous strains on the same farm. We used data here from MSHMP, and we identified 73 farms from that data set where there was at least 4 sequences available within a given year. And then we built time-scaled trees of that data and identified these farm-specific sequence clusters. So for example, this cluster of sequences is all from farm 21. You can see that they're closely related to each other and they're collected in a short period of time. So we would agree probably that this represents the circulation of a single virus on a farm at that time. And then we can look at the number of different RFLP types that are associated with that circulation event. And we found that 43% of these farm sequence clusters had an RFLP type change. There's a lot of instability in that RFLP type. For the variant system, we can again look at how many of these clusters had ID changes. We don't completely eliminate the problem, but it's a lot better than 43%. We also applied this variant classification to data from a specific production system to get an idea of how does this look like from the kind of the practitioner viewpoint. And so again, here we have 3 trees, all the exact same set of data or 5 data from the system. On the left, colored by lineage, in the middle by their variant ID, and on the right by RFLP typing. And you can see that the variant system gives us nice, well-differentiated clusters that align with the various different clades within this tree. So it seems to be doing well, and on top of that, this red bar here is a group of recombinant viruses from probably a single recombination event that left a large number of descendants. And the variants classification system was the only system that was able to give that group a unique label to identify that. Again, the RFLP types, there's 2 RFLPs that accounted for the majority of the sequences, and they're completely mixed up in the blue and the pink in the tree, which means that using RFLP patterns, it's going to be hard to discriminate between viruses on the same farm, what's new, what's different, and it's going to impact the detection of new introductions. This is a zoomed-in view of 15 farms on the landscape. This is from a single year in 2020. And so each of these dots represents a farm. on a map de-identified here. But let's take the perspective of a particular farm, which I've circled here, and how this system might work from their perspective. It's a 144 virus that was found on this farm. In the tree, you can see that the 144 viruses are kind of spattered around. But we can see that from the variant perspective, this farm has a 1H26, which identifies all those other related sequences, which are also 1H26s. If we look at RFLP types, there are 6 other farms that had the same RFLP type in this small area. And for the variant system, 1H26, there was also 6 farms that had 1H26. But it's not the same 6 farms, right? So if you're thinking about trying to determine the possible source of introduction or figuring out possible avenues of transmission, you're going to be looking at the wrong farms if you're using the RFLP type, which means that you're not going to probably be able to determine the correct route of transmission using RFLP typing. All right, so in closing review, just brief summary for me, what variant classifications can and cannot tell you. So variant classifications are more reliable than RFLPs at determining relatedness and whether virus A is the same or different than virus B. So this will allow for better discrimination between new and previous viruses in the same farm. And that will allow for more useful epidemiological investigations, such as determining possible sources of introduction or tracking between farm spread. What can variants not tell you? And this is important. No classification system out there right now gives you reliable information about virulence or clinical picture. And part of the reason for this is there's a lot of factors external to the sequence of that virus that are going to determine what happens and how that virus behaves on the farm, like co-infections, like the immunological background of that herd. There's a lot of other stuff going on that makes this prediction very hard. Classifications also do not translate directly into immunological cross-protection, although viruses labeled as the same variant are more genetically homologous. But we did not design the system to tell you those things either. We designed the system with the purpose of epidemiological monitoring, because that is what the practitioners told us in the survey is what they were trying to interpret from sequence data. So we really should be viewing these variant IDs as kind of a license plate, or specifically the state on the license plate. It tells you something about where you are in the overall diversity of PRRS. But it doesn't tell you every single thing about that virus. You know, you might want to do a whole genome to fully characterize that virus if it's of interest. But using variant classification is going to support the organization and findability of other additional information about a particular variant. For example, looking up, is there any publications on that variant, or is there any sort of case reports on a variant? And also, variant classification is going to support improved synergy and communication between research labs, diagnostic labs, monitoring programs, in the field. So we're going to pause here just for probably just a few questions, and then I'll pass the mic over to Dr. Yeske for the kind of practitioner view on this.
Questions?
Nobody else has one. I've got one, Kim. How, with this new classification system, I send my sample to University of Minnesota or the diagnostic lab. They get me 1HCXXX. Does that get done automatically by the D lab, or do we have to pay, is that an extra fee? And then right behind that one comes, what happens after that? Okay, I get the name of my virus, and then I want to start doing some epidemiology. How do I get the information to say, oh, the 6 farms? How does that come extra? How do we get that? Because it looks like the classification is so complex that we wouldn't have time nor the database, you know, to have that in-house.
Yeah, so, okay, I'll tell you what U of M VDL is doing. And right now, that would be part of the standard report that is given. So that would appear in the sequencing report you're getting from the lab. You'll get to that classification. And I know what our D-Lab is doing is that they're also taking the client charts for the last several years. I don't know how far they're going back, but they're updating all of the variants that might appear in your client chart if they're maintaining a tree for you or that sort of thing, to help you contextualize it. And so that would be basically the same information you're getting right now with our RFLP type. You get the classification, and then the additional, if you want to map it or do an epidemiological investigation, you know, those are things that would be handled either collaborating with an epi team, or a lot of veterinarians probably do that in-house. So a lot of that would be handled by that. The other thing I know that some groups are doing that do sequencing for clients is that they are also generating kind of a table that shows you, okay, this is the variant ID, and these were the RFLP types that you might find in that, to kind of help with them to transition, so they can know, okay, this 1H26, this includes things that are 184 or 144s, to help them kind of with that transition.
Hi, Dr. VanderWaal. I'm, excuse me, I'm Rabsa Nasir. I'm a student of Dr. Trevison's and Dr. Zeller's, so I've used your tool quite a bit. I was just curious, the data you use for the reference set for your PRRSV tool, is this something, are those sequences publicly available, or is that UMN data, the 2015 to present?
Yes, so the database that we use is the Morrison Swine Health Monitoring Project database, which is around 30,000 sequences, and they have around, they receive all sequences from systems that participate, so from sow farms and from growing farms. So, and so we think it's represented around 55% of the industry. And then one of the things that we're still working on is to get a few representatives per variant available publicly, so that for other research groups that want to go build trees and do those sorts of things, they can download a reference set. And we are we're still working on that part.
Right, yeah.
Yes.
And then one more question. Is your goal kind of to get other VDLs to start kind of using this nomenclature? Like, do you foresee this being something standardized with the variants of the variants?
Yeah, that's the vision of the working group, is that we would, all the D labs would be using the same system, and so we've really designed it. So for example, we have the assignment algorithm that you can use to assign new sequences. We have that algorithm available, and that can get ported directly into PRRSV, for example. And I know that talking to the great minds behind PRRSV is that they've actually already been able to do that, and so they already are able to implement it. And they, I don't think it's on their public reports, but they are getting the behind-the-scenes work done. And I've met with KSU, and they're going to, or maybe have already done it. They have a small sequencing caseload, though. The majority of the sequencing is probably being done by, 2 or 3 main labs. All right, okay, one more question, and then we'll pass the mic to Paul.
Thank you, nice presentation. This kind of classification can be useful for PRRS type 1?
Yeah, can we use this for PRRS type 1? So I was just at IPVS in Germany this summer, and we had some discussions on that, and sure, absolutely. There's no reason that you couldn't do this for PRRS type 1. My understanding, though, is that the nature of data sharing might be different, and where the data resides. So that they do not think in Europe, for example, that they have a good national, not national, I guess would be EU scale database in which they could do this with, like we have in the US. All right, thanks everyone. I'm gonna let Paul take over here.
All right. Well, thanks a lot, Kim. What my job was to come up and say, why do we need it? And some of the thought processes here aren't my own, but from our entire group at the Swine Vet Center. So a little bit where I'm gonna head with my portion of the talk is, one of the things as we sat on the working group, I told Kim, we can't we need a few names, but we don't need 10,000. And so we've got to figure out how to get this down to something that we can talk about and something that we can name it. And that was one of the advantages of the RFLP. At least we had a name for the viruses. How we can use it for PRRS breaks, PRRS closures, and then the new emerging viruses. And Kim's already gone through this, and I think, to me, being on the working group and seeing this evolve over time, we've certainly seen that there's a lot better definition with the lineage and variant versus the RFLP, and part of why we were having the confusion and part of why the working group was formed to begin with was to try and get rid of that confusion. Unfortunately, I said to Mike as we started the session here, I said I'm a little bit afraid to talk about PRRS in September. I'm challenging PRRS in an open public forum, and my D lab's going to probably, or my samples are probably going to show up positive tonight. But anyway, we're at the time of the year where there's not a lot of PRRS activity, and we're still at a relatively low rate. But the reason I put this slide up here from the Morrison Swine Health Monitoring Project is we continue to have, back here we had more episodic looks at PRRS, and we continue to have more PRRS living in that category 1, which, again, I think this is where we can use a tool to help us understand what's going on in those farms that are living in that category 1 stage. And we can see last year was kind of a unique year where the secondary spring spike was higher than the traditional October-November spike. And so, again, trying to understand if that's something new or if that's something that is just more circulation into the spring. And as we can see, it's been relatively quiet here through the summer, which we typically expect. But unfortunately, we can see a little activity starting here at the end of August. If we look at the SDRS data, which is a little different data, the other is reported from the farms, and the SDRS is from the diagnostic labs. And so, again, showing similar pattern here. We're at a very low level for the time of the year, which is always good. But one that certainly gives us a lot of heartburn here as we come to September. We see in August already it was starting to turn up, and we've just continued to turn up on the wean to finish. And if you look back here, whoops. If we look back here, you can see that that fall pattern shows up when the wean to finish, the sow farms usually follow within a couple month period of time. And looking at the SDRS data, and they're working to convert over to giving both the RFLP and the lineage at this point in time to kind of transition people. And I put this one up. It's a little hard to read for you guys out in the audience, but it just highlights some of the issues here. These are the same RFLP, but they're different lineages. And if you look here, there's different lineages and different RFLPs, and that was really the big part of the confusion, and everybody said, boy, this just doesn't work, and it's not very effective. And one of the nice things about the SDRS information is you can dial in by the month, by the year, you can dial in by the region and see where things are happening. And so, again, I think that's going to help us. This tool is going to help us to be able to utilize these tools even more as we do the epi work. And certainly we know PRRS has an impact within production herds, these being category 1, these being the negative herds. And so when we look at it and we look at the performance by PRRS status, and we look at farrowing rate, we can see farrowing rates a lot better on the negative herds. We can see born lives better. We can see that total weaned pigs per sow is better when we're more into the category 4 status. And when we look at nursery performance, certainly this is just looking at one subsection of data, but you can see that the performance is much better when we look at the average daily gain and feed efficiency. And when we look at the grow finish, we don't see as much difference in that average daily gain, but we still continue to see that lingering mortality differences there. And so part of where I see this going is we can hopefully be able to prepare or to be able to communicate better back and forth within our own systems and across systems. Kim met with our group, and she went back and looked at our own clinic-specific virus or sequences, and I was surprised on the number of sequences that were there. And so again, it's always interesting to go back and look at that over time and put together the trees for us. And again, you can see if we look at the variant versus the RFLP, you're getting much better definition. You can see there's a lot of intermingled colors here, and we're getting much better definition when we combined it looking at our specific viruses within our herds. And again, you look here, this is the RFLP, and this is the lineage. And so, again, a lot of color here, not much color here. So again, I think it's going to be a much more friendly tool for us to be able to compare farms without necessarily having to go to the sequence comparison chart. Give us a quicker down and dirty view. And again, here looking at the L1Hs, and you can see here, there's a lot more intermingled color, a lot better definition here. So as we talk about herds, we have really three options. We can allow the herd to remain positive, and you can see as an industry that's what's happening. We can go ahead and eliminate the field strain, or we can pass that and go right to depop, repop, and get the herd back into great production. Again, as we look at monitoring herd closures, because unfortunately we have breaks and we have to go back through these, we can go back and do the sequencing when we start to see abortions showing up or high pre-weaning mortality or other clinical signs. This is going to be a tool for us. Or if we're not making those milestones, and we do some sequencing to understand, are we still looking at the same virus? And if we start to see those clinical signs show up, again, the new nomenclature system, I think, is going to give us better definition to look at that quicker while we're waiting for the whole genome. I think the whole genome has become more important as we've looked at these recombinations, but this can give us a down and dirty answer early on. And to try and identify where we've seen some of these field viruses go, and then we have some of these recombinants back in the weeds, so to speak, and they show up later on as we get rid of the field strain and are a headache for us there at the end of these closures, or when we see some of these problem closures. And sorry, this gets a little bit small, but I put this slide in here. Here we had 3 different RFLPs, and when we put them on the lineage system, they're all the same lineage. So again, showing that confusion between the viruses, between the RFLPs, where it's hard to say, gee, is that 3 different viruses? Do we have a new introduction? And nope, we just haven't got the herd cleaned up. And the other use would be, and this is a study that Dr. Betlock worked on, looking at the use of killed vaccine. And as we look at these killed vaccine or where we're going to use these killed vaccines, how can we, if we're going to use an off-the-shelf vaccine, again, I think this lineage is going to get us to where we can get closer matches without having to go back to the genetic comparison and be able to line those up so we can potentially use the off-the-shelf products as we start to use this technology into some of our cleanups as we go forward. So in summary, at the end of the day, again, as Tim would say, we still know an awful lot about the truck that hit us. We just don't know enough to get off the road. And, and so the nomenclature just helps us know more about that truck that hit us, what kind it was. And hopefully the new system will offer us some advantages, and with better reliability and hopefully better expandability as we go forward. And the nomenclature, I'm sure, will continue to evolve as we learn more and more about PRRS and as we continue to battle it in the trenches. And with that, we can take some additional questions.
Hi, Paul. Thanks for that. Can you say a little bit more about how you think we might be able to use the classification system in the case of outbreak investigations if we're trying to determine
Sure.
Whether that particular source might be where it came from?
Yeah, absolutely. I think versus where we were in the past, just like that one farm where we were looking at it and we thought we had 3 different viruses and it was really the same virus. I think that can happen in areas too. And so in the past, we might not have looked at those other viruses being potential sources. So I think with the level of reliability and the level of definition you can see there, I think it's going to be helpful for us if we know those lineage and variants so that we can do that comparison as we're doing the outbreak investigation and looking at what's in the region.
Really good talk for and information. And I don't know if the question is for Dr. Yeske or Dr. VanderWaal, but are you thinking or envisioning to put any other variables in the sequence information like state, county systems, something that gives us a better perspective of how these strains are moving around?
Yeah, I can answer that question. So I think the question was about, are we going to be reporting spatial and temporal trends? I will say that the data that I technically use for this, I don't get space. MSHIP data is protected by a lot of confidentiality, so they only give the data that is needed for a particular purpose. That being said, MSHIP has the capacity and SDRS has the capacity to easily do state level, county level, whatever is appropriate for their respective uses, they'll be able to use these to report on those trends. So I would expect a lot of those mapping endeavors would be spearheaded by those sort of monitoring projects that are already in place rather than having a separate trend reporting.
And the SDRS today, you can already sort by lineage, and so you could look at that state. It would be at the state level, but you could do that by lineage today on the site. So I think long-term, that's where it's going to head to, probably to that level of definition until we go to a deeper level.
This is probably a question for Kim, Mike Rowe from Iowa State. Certainly understand OR5 and the amount of data that we have, but given the improvements in the chemistry and the equipment and the cost, is there any thoughts to expanding this to either whole genome sequencing or multiple genes to try to improve this even further?
Yeah, I mean, I think the challenge with there's a few challenges with whole genome. Once it gets more complex, and even though our turnaround time is improving, sometimes people want those really quick answers. And so for whole genomes, it's not just the turnaround from the sequencing, it's the bioinformatic complexity of looking at whole genomes. So I think that these OR5 kind of labels are, it's kind of like a license plate. It tells you maybe what state you're in, but it's not going to tell you everything about that vehicle or everything about the truck that hit you. But I do think that there is room for expansion. Like, I wonder if, given that we know recombination probably happens, like, do we take an approach similar to influenza where we have a few marker genes that would have that additional level of information that the H and the N give you, if something like that would be appropriate, but because it's not a segmented virus, it doesn't behave as nicely as influenza in terms of recombination. You know, it's just a little bit messier.
Thank you. Dr. VanderWaal, I think your group has presented before some things about looking at about an every 3-year trend or something about the variation or the emergence of a new lineage. Has this new sublineage classification shown anything about those trends? Do they still follow the 3-year trends, or has that been analyzed yet?
Yeah, so the question was about this pattern of every 3 years we see a new dominant sublineage. And so variants are smaller than sublineages, right? So I don't think that we fully know yet exactly, you know, if we look back at the peak of the 1A viruses, which includes 174, I don't know if when it peaked, how many variants at that point had it actually accounted for that peak. We haven't fully done all of that research yet to understand the interplay, and you know, looking at the 1C5s, or otherwise known as the L1C144 outbreak variants, you know, right now that's a really large group of viruses, and they're all still very closely related. So it's right now we're not at the point that we feel that we need to split that variant in some way because they're just still genetically quite similar to one another. So I think we don't quite know yet how that would relate, but we do know that there's every year there's probably 4 or 5 variants that emerge that are going to reach what we call common status, which means that they're detected at least 50 times. So we can see that every year on average, there'd be about 4 of those that would reach that common status.
I'm Antonio Viergo from Spain. I have 2 questions for Dr. VanderWaal. And the first one is, if you do the comparison between whole genome sequenciation against your classification, in variants and lineages, it is possible to better improve the accuracy if you do a whole genome, or the comparison between whole genome and this classification you made. What happens? In the same variant, you can have different patterns in other ORF or don't?
Yeah, okay, so yeah, the question was about recombination, and for sequences that are assigned to the same, OR5 variant, do they look completely different in a whole genome because recombination has occurred? I think that was the gist of the question. I've done some exploration where downloaded a bunch of whole genomes, assigned them to their OR5 variant, and then saw how different they are on the whole genome. And yes, it can happen, but because variants are smaller groups than lineages, it's not as much of a problem as it is with lineages, because we've done an analysis of what are the emergence times? By the time you get to a point that it's at a variant, you have 2.5% different amongst these different sequences. The most recent common ancestor was only about 2 to 3 years ago. So there's less time that recombination could have happened. So hopefully that, and generally they're going to hold up pretty well in the whole genomes, and we see that with the 1C5s. We have lots of whole genomes from 1C5, and they're all very similar on the whole genome. But they all say that they're recombinants, but they all share the same recombination profile. So I think that we should explore that further and see how often does the whole genome give you a completely different picture about if those 2 viruses are related. But I think it's going to be less of a problem with variants than it is for those larger groups of lineages and sublineages.
Okay.
And I have a second question: is how many sequences you need from European strains to do a classification like that? To begin to work with us.
Yeah, okay, so if we want to do this with European or PRRS type 1, I mean, I think that you would want something that you think is reasonably representative, and it might be easier to look at a particular country versus trying to do all of PRRS type 2, or PRRS type 1. So for example, even for PRRS type 2, North American PRRS, we've done this for the US. We've been talking about maybe doing it for some other countries that we have some collaborators with, but we haven't even attempted to do it in China, for example. But there's no reason that we couldn't, but it would take the right collaborator that has the interest in it and has access to some data. I would say at the minimum, to make it a reasonable place to start, I would think you would want like 500 sequences. But it depends on what's that time scale that you're talking about. Is this over a decade? Is it over a few years? And how many countries are involved?
Okay. Let's round of applause for Kim and Paul.